Welcome students, welcome to the next session of Strength of Materials 1. So in the previous class we have started a chapter which is bending stresses or the flexural stresses in the beams. There we have calculated or generated a pure bending theories equation, and then we have calculated section modulus for different sections. Later we came into the numericals. There we have analyzed for the stresses in the members which are symmetrical like rectangular, square or circular or symmetrical I section. Such type of members, what are the stresses in the top portion, in the bottom portion, nothing but the extreme fiber level we have calculated. And then we went into an unsymmetrical sections. So unsymmetrical stresses. So those unsymmetrical sections will have different bending stresses at the top as well as at the bottom. Then we have done an unsymmetrical I section. Even though it is I, but it is not showing with respect to the horizontal. So the above segment and below segment are not symmetrical. Okay. Now we are going into some more unsymmetrical section. As we have already given examples for unsymmetrical sections, simply I am going into what is unsymmetrical section, and then we are going into the numerical in unsymmetrical sections bending stress. Okay. So firstly, in case of symmetrical sections, what is the main difference for the symmetrical and unsymmetrical means? It is the neutral axis in the symmetrical sections is coinciding with the geometrical axis or geometrical center line of the section. So when we see any square or when we see any rectangular or when it is a circular or a symmetrical I section, when you see the symmetry both in vertical as well as in the horizontal axis. So when we see this left right, they will be symmetrical. Top portion, bottom portion, they are becoming symmetrical. Similarly for this, left and right are becoming symmetrical. Top portion, bottom portion are becoming symmetrical. Simply total height by 2, total length by 2. So that segments are becoming symmetrical. For this also vertical, same symmetry, horizontal also symmetry is there. And when we observe horizontal, top segment and bottom segment is the same alike, and when you observe vertical section, that also same symmetry is there. Such a type of symmetrical sections will have geometrical center line is being coincided with the neutral axis. Geometrical center line means this line which is at half the depth. Okay, so the geometrical center line is being located at half of the depth of the section, whatever is the section shape. Okay, so that total depth by 2 will be the location for the geometrical center line. Okay, so in this way all these symmetrical sections will have the neutral axis line, nothing but the centroidal axis line being coincided with geometrical center line. Geometry means with the shape there is a symmetry. So with the height there is a center line. So with respect to the height there is a center line. With respect to height there is a center line, and with respect to this height or depth there is a center line. That is geometrical center line. Okay. So that geometrical center line is coinciding with the neutral axis. But in case of the unsymmetrical sections, what are the unsymmetrical sections we have given? Those are L, T and unsymmetrical I. So such unsymmetrical I shapes, L shape or T shape. So when you observe those things, any L section or any T section or any unsymmetrical I type, maybe the top flange dimension and the bottom flange dimension are not same. Okay, such a type of members can be called as unsymmetrical sections. Why it is unsymmetrical? When you see half the depth, that is not symmetry. When you see half the length, that is not symmetrical. Here only left segment and right segment are being symmetrical, but the top segment and bottom segment are not symmetrical. Here top and bottom are not symmetrical, only the left and right are being symmetrical. Only about one axis it is showing symmetry, or it is not at all showing any symmetry. So such a type of sections which are not having symmetry in both the axes, about x axis, about y axis, simply along the horizontal, along the vertical, it is not showing symmetry. Such type of sections we call as unsymmetrical sections. They what happens? What is the difference for these two? In this, the neutral axis does not coincide or passes through the geometrical center of the section. So, total depth by 2. There will be a point. So, that point is not coinciding with the neutral axis of the nothing but the centroidal axis. As the section's centroidal axis is always coincides with neutral axis. But that neutral axis is not passing through the geometrical center. So, geometrical center line is not involved there. Okay. Such type of sections we are calling as unsymmetrical sections, and we have solved a numerically unsymmetrical I section also. Then we have observed a point. What is that? The neutral axis is simply passing through center of gravity, that we already know. And the value of y from the top fiber is different from the distance of the fiber from the neutral axis. Okay. So, when you see from the top fiber, there is a measurement of y to the neutral axis, and from the bottom fiber there is another measurement of fiber from the bottom layer. So, from the neutral axis to the bottom layer, the measurement is different from the neutral axis to the top layer. Whatever is the unsymmetrical I section, this is the thing happening. So, y to the top and y to the bottom. What is the meaning of y? Y is distance of the fiber from the neutral axis. So, distance of the fiber from the neutral axis. There is a layer is there. That layer is having a distance from neutral axis, that is y, and this y is different from the bottom's y. Okay. So, this y top and y bottom are different. Okay. For the unsymmetrical sections. Now, I am going into the another numerical that is involving a T section. Okay. So, a cast iron bracket T section. Simply we have already said bracket means simply a beam like structure I am using, but the T is made up of steel or iron. Okay. So, purely metal beams. When a beam is simply like a concrete one, when we call. In case of a steel or iron, we call it as brackets. Okay. So, a cast iron bracket T section as shown in the figure. Okay. The beam is simply supported on a span of 8 meters. Okay. So, when we see the length of the beam, that is 8 meters. When we cut the section, when we see the shape, that is T in shape. Okay. When we see, this is the length of the beam, that is 8 meters and it is simply supported. Okay. When we observe the cross section, in that cross section I am observing the T shape. So, this is the length of the beam and this is the section. So, in that cross section I am observing the T shape. And the beam is carrying, as it is a simply supported beam. This is a simply supported. So, it is carrying a uniformly distributed load of 1.5 kN per meter throughout the length or the entire span. Okay. So, complete length is having a UDL. When you indicate it with a simple line diagram, you can have a simply supported beam of 8 meter length being subjected to a UDL of 1.5 kilonewton per meter. Okay, so intensity 1.5 kilonewton per meter. So this is the thing happening. When we see the section, when we observe the cross section of the beam, that the cross section, when we see, this is the beam, and when we see the cross section, this is the shape. So that T shape is appearing in the beam. Okay, and we should have to determine what we should have to determine when these are the loading conditions happening onto the beam. Then I need to calculate what is the maximum tensile stress and maximum compressive stress occurring onto the section. Okay, we should have to calculate maximum tension stress and maximum compressive stress. How we will calculate tensile stress and compressive stress? As it is a beam structure and it is subjected to bending loading, and when I need to calculate the stress, we need to use M by I is equal to sigma by y is equal to E by R. That pure bending theory equation I need to use, where this M is involving maximum moment of resistance offered by the section or the maximum bending moment applied onto the beam. M is moment of resistance offered by the section. And the resistance chudisundi, that resistance is equal to the applied bending moment, maximum bending moment on the beam. Okay, and I is moment of inertia of the section. Okay, moment of inertia of the cross section about the neutral axis, and sigma is the corresponding bending stress, and y is distance of the fiber from the neutral axis. Okay, now this sigma is involving two types of nature, as our beam is simply supported and it is carrying some load. When you observe the beam shape, it will take like this. When you see the side view, the top flange is like this, as it is having a top flange line like this, and the beam shape may look like this. Okay, when you see the side view, this is the section, so you can observe the T shape, right? So this top flange and this T section, and the top flange is bending like this, and the T, bottom end of T is showing like this. Okay, so as it is a simply supported beam being subjected to UDL, it will give the shape like this, and this top portion will have compression and the bottom will have tension. Okay, so the bottom layer of this T shape will have the tension and the top portion will have the compression. Okay, so this is the thing I need to know, and I need to calculate what is the maximum tensile stress in the material due to the given load, and I need to calculate maximum compressive stress in the material due to the given loading condition. And firstly, like we have already said, if it is a symmetrical section, without any doubt, I am going into the calculation of M answer, calculation of I answer, and then I will go into sigma and y. But when it is an unsymmetrical section, for calculating I, moment of inertia about the neutral axis, for that answer, first we need to locate the neutral axis, where the neutral axis is. Generally, for the symmetrical sections, neutral axis is at half the depth. So, without finding the location of neutral axis, I am directly going into moment of inertia. But in case of unsymmetrical sections like T or L or unsymmetrical I, first for evaluating the I answer, moment of inertia about the neutral axis answer, first we need to locate where the neutral axis is. So the step 1 is locating the neutral axis. Okay, so we should have to locate the neutral axis. So we already know the neutral axis is coinciding with the centroidal axis of the section. So neutral axis is always coincides with the centroidal axis of the section. Okay, now we are writing from base level. Okay, distance of the centroidal axis from the bottom or base I am measuring. Okay, and as this is the baseline reference, and I am taking this portion as 1 and the vertical member as 2. Okay, now this one area of this one portion, how much it is? 100 by 20. Okay, so 100 by 20 into, that is the area of the first portion, and into what is this y1? Y1 is distance of centroid of the portion from the base, because I am measuring from base. So from base of the T flange. Okay, from the base of the T flange, this is T end. Okay, so from the base of the T flange, distance of the centroid of this position, how much it is, that I need to calculate, and that is equal to this value and summation of this value, right? So this portion plus this portion, summation of this will be the answer. And the bottom flange is having 80 mm, the web is having 80 mm measurement plus, and from this top I need to give half, as it is a 50, so 50 by 2. Why it is the summation? Because from the base I know up to this measurement, that is 80, and this measurement is total 50 by 2, so that 25 I should have to add. So A1 by 1, and plus what is the next area? That is the second segment's area. Okay, so this rectangular portion. And for the portion, what I need to indicate? We need to write the area into centroidal location and the perpendicular distance. So area portion, what is the area? 80 height, only from this level to the bottom, 80 height and 20 thick. So 80 into 20, or you can write 20 into 80 also, whatever it is you can know. Firstly, generally we are writing horizontal and then we are writing vertical. So first horizontal 20 and the height is 80. So B by D, like that we will write. And then I need to multiply it with how much measurement I should have to multiply, as it is 80 mm and at the center only the location will be there, the centroid location of the part rectangle. Okay, only this portion of rectangle is there. That portion's rectangle centroid is at 80 by 2 from the baseline. Okay, A1 by 1 plus A2 by 2 by A1 plus in this way I am calculating by bar. So the centroidal location of the T section from the baseline. Now the value I have got as 67.77 mm. Simply the calculation of this value. Okay, so simply calculating this answer, I have got the measurement as 67.77 mm from the bottom or base. Whatever the word you use, that is okay. Okay, from the bottom or base. And the position indication is important. Okay, Y bar, it is okay. So in a sentence way, I am writing therefore the neutral axis for the T section is at 67.77 mm from the bottom. Okay, this is the location. It is very important. Not with the value. That value is measured from where. That indication is important. Like when we do in the shear force and bending moment diagrams, the shear force is 0 at some point. Okay, from which position you should have to indicate, or the bending moment or the point of counterflexion is there. Okay, where is the point of counterflexion is located? From which reference? Okay, that reference or the location we should have to give. So this statement is important. And then after getting the neutral axis location, we should have to calculate the moment of inertia of the section. Now we have given the whole picture. The original T section with the original flange dimension and the thickness of the flange, and the remaining height is 80 mm web and the corresponding 20 mm thickness. As from the baseline, the neutral axis is being located at 67.77 millimeters. So the neutral axis is indicated like that. You can write NA. NN is indicated for the neutral layers. Okay, neutral axis is section lines line. Okay, neutral axis NA is like this, and the top remaining measurement also, that is important for us, right? So for the reference I am writing 80 plus 20, that is equal to 100 mm total. That 100 mm minus 67.77, that is from the top. The remaining is 32.23 millimeter from the top. So the neutral axis location is at a distance of 32.33 millimeter from the top line. Okay. Now I am going for the calculation of moment of inertia about the neutral axis. So for entering into moment of inertia about the neutral axis, I should have to indicate there are 2 parts, 3 parts. How many segments individually are there? Then we will get enough clarity, and summation of all those moment of inertias will give the final output. As the top portion is like this, neutral axis line, and we are having 100 mm and 20 mm, and the measurement just now we have got as 32.23. Okay, so from the neutral axis line That is the distance. That is the top portion's distance. 100 by 20 is there, right? So only the top portion I have written. That top portion's moment of inertia about the neutral axis I should have to write. As this portion is not passing through the axis, it will involve parallel axis theorem, Ixx plus A into y square. Okay, what do you mean by Ixx? For that sections B d cube divided by 12 plus ay square. Okay, what is this B? Which is parallel to the dimension, that is 100, and which is perpendicular to the axis, that is 20. B d cube divided by 12 plus 100 into 20 into the distance y. Y is indicated here as distance of centroid of the portion A from the neutral axis. Okay, so as it is 32.23 is the measurement I know. Okay, that is the 32.23, and minus how much I should have to remove? The remaining, this portion I can remove for getting the value, as I know the total and I know this height. What is that height? That is 10 by 2. So 20 by 2. This is 10 mm. So 32.23 minus 10 mm is the from this point to the neutral axis distance. Okay, from this point to the neutral axis measurement. Only B d cube by 12 plus A y square. Don't forget to put the square. Okay, I am substituting the y, and then I should have to cross check B d cube by 12 plus A into y square. I have given or not. Okay, with this value we will calculate only for the top flange. Now I am going into the web. So this web is like this, with a height of 80 mm and with a thickness of 20 mm, right? And we are indicating the neutral axis location, which is at 67.77 from the baseline. Okay, so that is the neutral axis line for the second section. 67.77. Only I am writing the second section only. Initially I have taken up to this portion, I am taking the second portion. Now I should have to write the moment of inertia of this portion about the neutral axis. If it is its own centroidal axis, okay, if this neutral axis is its own centroidal axis, I can simply write B d cube by 12. But what is the centroidal axis of this line? That is at 40 mm from top and 40 mm from bottom, right? As it is 80 mm line, so from 40 and this is 40. In this way, the original centroid will be there. So the original centroidal axis is not passing through the neutral axis of this segment, only this portion. So again parallel axis theorem will come. Again Ixx plus ay square, that is equal to, again it is a rectangle, B d cube by 12 plus A times y square, and what is the B? B for the segment is, which is the line passing, parallel to the axis line. That dimension is 20, this dimension, and the height dimension is 80. So B d cube by 12, again area 20 into 80 into what is y? Y is distance between the considering axis, about which axis I am taking the moment of inertia, and this is distance between the axis and the centroidal axis. Okay, distance between the axis and the centroidal axis. The remaining measurement is the perpendicular distance between those two. So that is 67.77 minus 40 mm. Why this 40 mm came? Because this 40 mm is equal to 80 by 2. In this way I have got 40 mm answer. And we have got the multiplication. This is ay square. In this way we have got y1 and I1 and I2. Summation of these two moment of inertia about the neutral axis is I. So capital I is moment of inertia about the neutral axis. We have got this answer. And then I am going into just further theorem. What is the pure bending theory? That is giving the equation m by I is equal to sigma by y is equal to E by R. Leaving the last term and taking first two terms only. M by I is equal to sigma by y. There capital M is needed to be calculated because they have given the loading answer. They don't have given the maximum moments answer. Okay. And capital I is moment of inertia about the centroidal axis. Okay. Then y is becoming y maximum, sigma will become sigma maximum as you already know. And when I am substituting distance of the fiber in the compression phase, the corresponding compressive stress will come. Similarly, distance of the fiber in the tension phase, the corresponding stress in the tension zone will come. So, m by I into yc will give sigma c, m by I into yt will give sigma t. And the answer for capital M, how the capital M comes? Capital M is equal to maximum bending moment occurring on the section as our simply supported beam of length 8 meters and being subjected to UDL over entire length. See here how it is. We are having a UDL of 1.5 kN per meter. So, a simply supported beam with UDL over entire length, the maximum bending moment is WL square by 8 and we have got W intensity as 1.5 kN per meter into 8 square by 8. In this way, we have got the maximum moment as 12 into 10 power 6 Newton millimeter. Here our units are in meters and meters only, right? This one is not value, simply a constant WL square by 8 we have got. Okay. So, this kilonewton per meter into meter square. So, we have got kilonewton meter answer and this I am converting into Newton millimeter by multiplying it with 10 power of 6. So, either I can write 12 kilonewton meter and for the use I am writing as 12 into 10 power of 6 Newton millimeters. Okay, so the multiplication of Newton millimeter we have got. And this is capital M calculation over capital I calculation also over. YC and YT, yes, we have already got YC and YT are coming from the distance of the fiber from the top layer and the bottom layer. As it is being a simply supported beam, the bottom phase will be in tension, the top layer will be in compression. So, this measurements we call it as this value is compression phases distance and this value is tension phases distance because in the bottom only tension zone comes. In the top compression zone comes as it is a simply supported beam. Okay, YC values, YT value, capital M and capital I we have got. Substituting all these answers we will get sigma C and sigma T. Firstly, what is capital M we have got? 12 into 10 power of 6. So, this 12 into 10 power of 6 Newton millimeter divided by what is the moment of inertia of the whole T section about the neutral axis? 3141,333.44. This one is in mm power 4 into we have said compression phase. So, the compression phase is at the top, that is 32.23 millimeters. So, multiplying all these things, we have got Newton per mm square as the sigma C's answer. Similarly, keeping all the things the same, only changing the distance, we have got and the corresponding tension zone's distance, that one is the value we have got as 67.77 millimeters. And overall stress in tension zone is equal to 258.87 Newton per m square. If they are asking for any other thing, what is the highest value? You can simply say as Yc is a lesser value than Yt, I have got this as lesser value. So, maximum stress occurring in the tension zone, compression zone. Maximum stress that can be occurring in the tension zone. These two are the answers. Okay. In this way, we will calculate different stresses in the top fibers and in the bottom fibers. In overall, in this flexural stresses or the bending stresses, we have generated our equation M by I, sigma by Y, and that which is equal to E by R. And here, capital M is moment of resistance offered by the section. If they are not giving the M answer, how we will calculate? M answer is simply maximum bending moment occurring onto the section. So, the maximum bending moment formula we already know for the different loadings. So, that maximum bending moment we will substitute here. And I is moment of inertia about the neutral axis. If the section is symmetrical, I can directly calculate. If the section is not symmetrical, we should have to locate neutral axis, and then about the neutral axis, we should have to calculate the moment of inertia. And then this is sigma, the corresponding bending stress for the Y value. And E, Young's modulus, and R is radius of curvature. Now, these two terms we may not be using. These two terms are very important for us. Okay. In this way, we have calculated stresses in the flexure or bending condition. In the next class, we will continue the topic with shear stresses. Thank you.